And we're back. All right. Welcome to the continuation of the heat of formation lecture.
Part 2.
Anyway, I was saying something.
That could have been bad.
So now, if it's combustion, the 1 mole rule applies, but it's going to be one of the reactants. So let's do methane again, which is going to be my CH4. All right? And remember, since it's combustion, it will always follow the rest of this sequence. A hydrocarbon reacting with oxygen to produce carbon dioxide and water. And now we're going to do the exact same thing we did a moment ago. The method right here. Practice, number 1, methane. The first one was methane, but that wasn't combustion. It was just the heat of formation. Now I switched it to combustion, which will put our target, our focus, as a reactant instead. Because by definition, combustion always adds oxygen to a hydrocarbon. All right? So, now we're in a situation where we can't alter him. Remember, there's always one item in these problems that you can't touch the coefficient of. 1 mole of him, so here we go. My carbons are good. My hydrogens are now good. 2 oxygens plus 2 oxygens is 4 oxygens. Now we're good.
Yeah, on the same page.
Where'd you get it? Oh, you switched them.
Didn't you say you couldn't touch the reactor?
You cannot touch the item that's combusting,
Oh, okay.
which is just him. There's always only one item that has to stay at 1 mole. Now, that was another easy one. Let's do a more challenging one. Take a look at number 2 here. It's still combustion, so it's going to go... What do we got? C3H7OH. C3H7OH. Can't touch his coefficient. It's combustion, so he's going to react with oxygen to produce carbon dioxide and water. Yes. So now let's make our enthalpy of combustion correct. The carbons I can fix. Boom. How many hydrogens are there?
8.
Hydrogens I can fix. Boom. See if you can put in the one thing I have not fixed yet.
That's fun.
You can never do decimals. You can only do fractional coefficients. Decimal coefficients will lose you points. Let's go over to cluster 3, seat 2. Here, let's do it together. Let's do it. How many oxygens are there over there? Oh, there's 10, all right? How many oxygens are there right there? Sorry, how many? There oxygens above my... There's 1 right... Okay, I see what you did. There's 1 right there, all right? So to get to 10, I need this to equal 9, right? No idea where to go from there? Take whatever number that you need it to be and put it over 2. The answer is 9 halves. Because 4.5 times 2 is 9 plus 1 is 10.
You can't have
I was talking to everybody on that last thing. I wasn't looking at you.
But why can't we have decimals? Like
Because I am the god of chemistry, and I said no. And on day 7, I rested, so shut up. We all right?
Yeah, we're good.
All right. So what we can do now is continue yesterday. You needed this skill in order to do the other 3 ways of calculating enthalpy. What? It was 1 to 9 halves to 3 to 4 was the mole ratio.
Oh, I thought that was a 1.
I'm going to shoot it down.
All right, guys. Hess's law is something that some of y'all are not going to like. Some of it kind of feels like mechanisms, when we were looking at kinetics and we were having to cancel stuff out. So really focus if you struggle with that at all. I'm not going to read this screen. You can read it. It just explains what we're about to do. So let's take a look at how to use Hess's law to find enthalpy. Now look here. Do not be copying that screen. That makes me mad at you.
I'm writing.
No, I did not look at you a single time. Anyway, to do Hess's law, here's what they're going to do. They're going to give you the heat of formation for some different compounds. And then you're going to have a goal reaction that you're supposed to find the enthalpy for. By looking at the relationship between the given heat of formations to the goal reaction that you're analyzing, you can come up with the enthalpy of the reaction that you care about. Look at this example. Those top two are just giving us enthalpies of formation, all right, heat of formations, I'm sorry, for two reactions that we're not even really analyzing, but we can use them to figure out the enthalpy of our goal, the one that we actually care about. Some teachers call this skill the flippy thing. I don't like saying that phrase. So we're not going to call it the flippy thing. We're going to call it Hess. But you can flip and you can multiply and you can do whatever you need to do to the top reactions to make them equal the bottom one. Let me show you what I mean. If I look at that very first reaction, I'm looking right here. Make sure you've got your slides. Look at the topmost reaction for Hess's law. If I compare it to the goal, that's the goal down there. If I compare him to him, here's the first thing I notice. The CO, the carbon monoxide, is on the wrong side of the equation. Do you see that? So what can we do to make them the same? We can flip it. So what? We can flippy thing. Okay, so if I flip it, you're working with me, it would read like this. It would read CO gives me C plus 1/2 O2. All I did was flip it. Do you agree?
I agree.
Hey, what happens to the heat of formation if I flip the reaction? It changes the sign. So instead of it being negative 111, it's just 111. No, well, I did. I mean, really, I flipped the arrow is what I did. But I just wrote it clear. All right? Cool. Let's look at the second reaction, all right, in comparison. All right? Hey, look, the second reaction looks all right to me. All right? There's nothing that needs to be flipped. Everything is where it belongs. All right? So what I'm going to do then is just write that reaction the way it is. I don't need to alter that one.
Why don't we have to alter it again?
Because if I compare the second one to the goal, there's nothing that I need to do to make it better.
I don't get the first one to goal.
It does. You're right. It does it because we're going to need both of them. I'll show you how we're going to make them match. All we can do is incrementally get them closer to each other. Now, that negative 394 is not going to change because we didn't flip or do anything. All right. So all I've done is all I've messed with so far are these top two given heat of formations. That's all I've done.
So are you not trying to make them the exact same as the bottom?
So here we go. They are the exact same now. Watch. Here comes some mechanism action. Remember, if you find something in your list that is the exact same as reactants and products, they go bye-bye. They go bye-bye. Watch. Dun, dun, dun. We've got carbon and carbon. And look, the O2s are identical to each other. All right, it's just I have more of this one. But we can, if you remember back in mechanism, as long as the items were exactly the same, you could cancel out as much of them as possible. So I can get rid of half an O from each. I can get rid of half an O there, and I can get rid of half of this one. What will this become if I get rid of half of it?
Half O2, so 1 O. That's CO plus 1/2 O2 equals CO2 to the bottom.
CO plus half O2 yields CO2, which is my goal.
Oh my gosh.
Now, we haven't solved the problem, though. All right? All this did was prove that these steps were correct. The final step's real easy. In order to find the information at once, we're going to add together all of the heat of formations. And if you add those two numbers up, you will end up with, I don't feel like doing it, so I'm going to cheat. Negative 283.
Wow. Cheated.
All right? Now, I know that was a little clunky, so we're going to do another one. But again, your goal That's a bad word to use. What you're trying to achieve is to look at the given heats of formation and alter it to eventually match your goal. Let's do a harder one. Now, this one is mean for several reasons. First off, it doesn't give you a goal. It assumes that you know how to write these equations, so we're going to have to write our own goal equation. Look at the bottom what it wants you to analyze. 1 mole of combustion. So let's make sure we remember what that means. When it was combustion, the item that we were analyzing was a reactant, right?
Yes.
And only 1 mole of it.
Oh.
So it's messing with ethane. So what I'm going to do is write our goal reaction down here. All right? And it's the combustion of 1 mole of ethane. So here we go. C2H6. It's combustion, so plus O2 is going to give me carbon dioxide and water. Who just left? All right, let's fix that because we're not balanced. All right, carbons, boom, hydrogens, boom, oxygens. There's 4 and 3 is 7, so 7/2. Now, all I've done so far is found the goal equation that I'm going to use the others in Hess's law to make it equal this. All right.
Let's do some math.
So here comes the fun. If I look at the very first equation, what strikes me, and I hope it strikes you, is that the product is what I need to be the reactant. Do you agree? So let's flip it. Let's go C2H6 yields 2C plus 3H2. What will that do to the heat of formation?
84.6.
It'll flip the sign, so now it's just 84.68. Are you with me?
Yes.
Hold on, I'm very confused. The goal reaction isn't given, right?
Right, so we made it. There it is.
Oh, so you just
That's
say
what we
how?
had prior knowledge.
Exactly. That's why I taught you the prior knowledge prior to the problem. Prior.
Exactly.
All right, here we go. Here we go. Let's look at the second one. Now, hey, things about to change. Look, on the second one, the carbon dioxide is where it needs to be, but there's the wrong amount of it. How many carbon dioxides do I need?
2.
So what do we do to fix that? If we multiply the entire equation by 2, it'll make that work. So watch what I'm going to do. To that second one, I'm going to go 2C. I'm multiplying it all by 2. Plus 2O2 yields 2CO2. Now that's the exact same problem, but what do you think that just did to the heat of formation? It doubled it. All right. Now that heat of formation is sitting at negative 788.
It's like basically what you must do to one side, you must do to all 3.
All right. Cool. We've got one more to look at, and if you look at the third one, you'll notice that the water is in the right place, but we need 3 of them, and there's only 1 of them. Let's multiply all of the parts by 3, and you'll end up with 3H2 plus 3 halves O2, that was fun, yields 3 waters. Is everybody okay with 1/2 times 3 being 3 halves? Yeah? So it'd be a half and then a whole and then a 1 1/2. Anyway, yeah, so times 3 to the heat of formation, and you get negative 858. Now, here's the most important thing. I don't have time to misguide us into mistakes to show you how your brain should fix that. I don't want you to think that you can't mess up in what we've just done. You can. All right? The way that you are certain that these are the numbers you're supposed to add together is by doing this cross-off part. All right, the cross-off part's not really a part of any work you have to show, but if it doesn't equal the goal, then something is wrong over there, and you might have to go back and just alter something different. All right? But since I didn't have time for that, you'll notice that this is going to work. 2C and 2C, 3H2 and 3H2, nothing else matches. C2H6 plus 2 and 3 halves is the same thing as 7 halves, O2, yields 2 CO2s and 3 H2Os.
Wait.
Wait.
KJ.
You're the opposite.
Add them up and you're done. The final answer to the problem here is going to be negative 1561. Ow, roughly.
Does it matter with secrets or you just...
No, you're right. Yeah, ask.
The oxygen. Oh. No, I don't know.
Well, it's the oxygen is 2 and 3 halves. That's a mixed fraction. 2 times 2 is 4 plus 3 is 7 halves.
Oh, so it's not like 2 times 2 is 4 and 4 plus 3 is 7?
I mean, I can't. You don't remember how to do
I
that?
don't. No.
Just do 2.
In order to turn a mixed fraction into this, it's the denominator times the whole number plus the numerator. I can't take you back to middle school.
So it's not 2 times 2 equals 4 and 4 plus 3 is 7? That's just a coincidence?
No, yeah, it is. That's what I just said. Yes, that's exactly what I just said.
Okay, I'm just saying, because that's what I did, and it was 7, so I was like, cool, but it's not going to work every single time.
All right, let's move on. All right, we've got 2 left. We've got 2 more ways to find enthalpy, and here's another real important reaction. This slide got all jacked up. I'm sorry. This is supposed to be here, and there's writing missing down there, but I'm about to fill it in for you.
Oh, mine was fine.
Well, maybe yours is fine. I hope it's fine. Okay, good. Can I erase?
Yeah.
Okay, so Big Mama. All right, this equation doesn't have a name. We're going to call her Big Mama. Those are sigmas that you see. A sigma refers to finding the total sum of. What we're going to do for enthalpy here is we can use heat of formations that are given to you in the table in order to find all of the total heat of formation of the products minus all of the total heat of formation of the reactants, and that'll give you the heat of the heat of formation of the entire reaction. All right. This thing down here that you can't read points out that if it's a free element, it has no heat of formation. Free elements have no heat of formation. You don't even really have to memorize that. I mean, it's good to know, but you'll notice that there's never free elements in the tables that I'll give you, and it's because there's 0. So how do we use Big Mama? I think you'll think it's easy. Exactly. Yeah, and this is the only table I've ever found that actually lists them as 0. So there you go. But the other ones aren't going to. All right. So remember, listen again. In order to do this, you add up all of the products minus adding up all of the reactants. All right? So let's use Big Mama. I'm just bringing it down for the video. And let's start with the products. All right? Now, one thing that we need to remember, though, is that heat of formations always give you values based off 1 mole. So what will the coefficients in these reactions have the ability to do? To multiply. All right? So, for example, we're starting by looking at the sodium hydroxide on the product side, but there's 2 of them. So I need to be saying, all right, well, there's 2 NaOHs with a heat of formation of negative 470. I'm supposed to add that to the other guy. All right, there's only 1 H2 with a heat of formation of 0. I hope that you never ever write that again the way that I just did. It's not wrong if you do, all right, but this is pointless information because it's not going to alter your answer. But just so you can see where it comes from. You okay? Yes, products minus reactants.
So it has them listed like the states of matter. Is that ever going to have any effect on anything?
The states of matter, all states of matter are eligible for this, but the heat of formation of liquid water is different than the heat of formation of gaseous water. So yes. Minus, all right? Remember, it's the sum of, but you're subtracting the data sets. Now the reactants. There's 2 sodiums, but it's 0. I'm not writing it because it's ridiculous. All right? But there's 2 waters sitting at negative 286. Plug and chug, y'all. Hey guys, one function. Do it as a singular function. Order of operations can be evil. Just like you. What you say? I get negative 368.
Yes.
Wait.
What's this again?
You know what I miss? Kilopascal. Those things are cool. What cool name?
This, the heat of formation. Heat of formation.
Oh, I see what I mean.
And all that formation does is it adds in that mole part, but it's enthalpy. All right, this is a change in heat, is what it is. All right. All right, this one is highly repetitive. How much time do I have? Do I want to be repetitive?
You got 12 minutes.
35.
What was that sound?
Here, I'm not. I don't want to be repetitive. I want to make sure I get through everything. So we're going to do another one that's a little tougher. But guys, this one's the exact same. Notice that it doesn't give you the heat of formation of the oxygen. Why does it not give it to you? Because it's 0. So that's what it's usually going to do. All right, so it would be 2 CO2s, which is the negative 393. All right, plus 3 waters. That's your data set, and then minus the 1 reactant. All right. Now, the problem we are going to do uses this same table. So have that slide in front of you as Isaac brings up the next problem.
Thank you.
All right, here we go. The reason I like this one over the last one is that this is the exact same thing. It's Big Mama, plug and chug. But instead of you missing the heat of the reaction at the end, all right, it gives you that. You're missing one of the interior values. So it's just different algebra, but let's go through it anyway. We're going to use Big Mama. I'm going to start with the products. Therefore, we're going to go 6 CO2s. If you look back, you'll see that CO2 is sitting there at negative 393.5. It's from the previous slide. I add that to the other product, which there's 6 waters. Water was negative 285.9. Minus the other data set, which there's only one item over there, right? The oxygen's a free element. It's 0. Who cares? But we're not given. It flat out says calculate the heat of formation of him. In other words, he's X. We don't know that number, but it does tell you what the heat of the reaction is, negative 3924.
This is nice.
Be careful. Solve, but be careful. I'll draw a card in just a moment.
We didn't put O2 because it's a free element. It's not on that list because it's 0. Free elements always have a heat of formation of 0. But it's all we have. So if you're not adding any other values from anywhere, then you
That's a great word. We call it Google. If I were to have a competitor, I would want to be named.
Sorry. No leadership.
Bang.
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 Bing, bang.
Bing, bang, and then we'll have like a third one called boom. There we go. I want to make progress.
What? I did not get that. What do you mean? I'm confident in my answer. Unless I mean, I can't do fractions. But then again, I can. That's what I'm saying. I hate that you.
I love better.
Good for you. Hate that guy. He's a cool person. That class
Kevin
is
from
stupid.
Fred the movie.
Don't talk to me.
Kevin, the blue skyline.
When did I say Kevin?
I don't know why I heard Kevin, but I'm thinking
Kenner.
Oh my god, it's dice! Let's go over to cluster 1.
Is that us?
Yeah, this is your seat there.
No.
Seat 4. 1-4. Would you like to share your answer with us?
Calculator, I couldn't do it.
You are seriously sitting there chatting with that girl.
My calculator's
You could have
dead.
done numbers.
You could have, there's a calculator on your desk.
No, but I fixed it.
What?
You're an 11th grader. You cannot do it in your head. Yes, sir.
Will somebody help Robin, please?
It is.
Anybody?
Oh, negative 152.4.
That's correct.
Big mama.
Go, Big Mama!
Stop that shit.
Stop. I'm recording.
He's gonna get the money.
I'm recording.
Is that gonna get any money?
Edit it out. You actually.
No, this is dumb as
Yeah, because that's what I have time to do is go edit out all your swear words.
We don't do swear
For a pizza box, I'll do it.
SpongeBob.
There is one last way to calculate enthalpy, so let's do the last one.
I have it given to you.
Okay, we're good?
Nope.
Oh.
I just did the whole thing. Okay. Bond energy is the last way in order to do this. Now, the good news is that bond energy, when you're looking at bonds breaking and the amount of energy that they give off or take in, it feels a lot like Big Mama. But when you're looking at the heat of formations from the perspective of bond energies, the reactants come first. So it's going to feel exactly the same, but you'll see it. Some of the bonds broken minus some of the bonds formed. That's going to be reactants minus products, based off a given table still. Now, look here, though. Here's what they're going to do, though. They're going to give you a table that shows actual things bonding to things. It's going to say when H bonds to H, it's this much energy. And when H bonds to O, it's this much energy. And when Cl bonds to Cl, and you're going to look at that. Sometimes the problems are going to be simple, like the one that we're about to do. But sometimes what they'll do is they'll give you a big drawn molecule. And your job is going to be to count all of the OH bonds, and then go count all of the Cl-Cl bonds. And if you get the count wrong, you're going to input the information incorrectly. So you've got to be real careful while you're doing this. But just so you can see what a problem looks like, Isaac. So, I didn't do the picture thing here. I just give you a reaction. Hydrogen reacts with fluorine to give you hydrogen fluoride. And then you've got your table. Now remember, for bond energy, it's the sum of the reactants minus the sum of the products when you're looking from this perspective. So what I'm going to do is the exact same thing. I'm going to say, all right, Well, there is one H2, which is just an H bonded to an H, right? So it's that item at the top, 432. Plus the other reactant, which is 1 F2, 1 F2, which is an F bonded to an F at 154. Minus the product, which in this case, there are 2 of the HFs, an H bonded to an F, so that's just 565. Because when you're looking at the energy from the bonds perspective, this is the only way to actually track the heat the correct direction based on the side that we're breaking bonds versus the side that we're building them. Nope, you don't.
Wait, so are they always going to be the composition, or can it pick? Like,
Oh, no, it could be the other way.
how do you know which way to go?
Very successful today.
No, hold on, wait. We haven't put an answer down. No, all of the problems, you're right, all of the problems in this course are going to be synthesis for this.
Like a synthesis essay.
Y la silencio.
Anybody have an answer?
Negative
544.
Negative 544.
I got that.
Wow, good job.
Slash mole. Sorry, slash mole. Sorry, there's 2 videos.